General relativity, step by step. I got a bit carried away in the last screencast, and all I wanted to do really was to show that this quantity here is not a tensor, but it behaves as though it is one to the order of approximation that we're working to, which is the first order. And one of the ways in which it does behave itself is the fact that it transforms under the Lorentz transformations nicely. And I'm going to introduce another class of transformations which in which the transformations work as you expect them to work. I'm going to consider small perturbations. I'm going to consider a barred coordinate system which is equal to the old coordinate system plus some small function psi alpha of x0, x1, x2 and x3. So that's the new barred coordinate system. It's equal to the old plus some, of course, small function of the old coordinates. This is a letter psi, psi. It's this kind of curly one. It's got a nice uppercase letter that looks like that. Nice Greek letter to use, X. What did I want to say about this? Oh yes, sometimes you'll see the same relationship written like this. X, oops, that should be an X, plus psi alpha of x beta. I'm not sure if I like that notation. You've got this beta sort of hanging free, but as we'll see, when we've got this very specific class of transformations, the usual laws of tensor algebra don't really apply. Well, it's not that the rules don't apply, it's just that the usual considerations for well-formed tensor equations have to be modified somewhat. You will also see this notation used here, x alpha bar, let me just write it out, plus psi alpha of x beta. Here, of course, the bar is being written on the index to signify that it's the new coordinate system. Sometimes I'll use that notation. I might resort to it. I'll see how things go. Okay, but I'm just going to say x bar alpha equals x alpha plus psi alpha of x beta. Right. This is small, and also its gradients are small as well. So if we want to use this transformation law here to transform our tensor H, our supposed tensor, my pen, there we go, H alpha beta, we need to work out what di x bar alpha by di x beta is. Well, that's di by di x beta of x alpha plus psi alpha of x. I may as well put the, do I want to put the beta in? No, I'll just leave it as a sort of free x. Actually, no, I'll write it out. x0, x1, x2 and x3. Well, that's just equal to the Kronecker delta alpha beta plus di psi alpha by di x beta, and you may as well write that using common notation as delta alpha beta plus psi alpha comma beta, and that is di x bar alpha by di x beta. Well, that's great, but if we want to transform freely, we're going to need to work out what this character is here, di x bar beta. You see here we've got the bar on the top, and there we've got the bar on the bottom. I'll do that in the next screencast, but for the moment we've got this nice little transformation, and I want to work out the opposite one here, and I'll do that in the next screencast. Stop.